that's the trick. Okay, D, pair of balls. This one's interesting. It's yeah, pair of balls, both of them a pair of balls. Oh yes, sliding along a long horizontal frictionless groove, so we're not losing anything due to energy and all of that friction. That is, energy due to friction. The frictionless groove towards a stationary third ball, also of mass m, as shown in the following diagram. For the collision of a pair of objects, the coefficient of restitution is sigma, small sigma, is calculated by sigma equals the difference of velocities after over the difference of velocities before. And the coefficient of restitution of these balls is 0.4. Show that there are just 3 collisions between the balls and the sum of the final velocities is 8 meters per second. Well, okay. You could do this a number of ways, well, 2. You could actually go straight to the final bit and show that by, because the mass, in fact let's do this, yep, because the mass of all 3 balls is the same, okay, mass times 3 is the same, this is just my rough notes, that means, and if momentum is conserved, which we know it has to be, then all of your momentum equations become velocity equations. So velocity is conserved, since they're all the same mass. Okay, I don't know if you can see how that works. So now you can set out to prove that by using this formula. And what you're going to find is there are 3 collisions that will take place, and all the balls will end up going in the same direction, with C having the highest velocity, B having the next highest velocity, then A having the next highest velocity, and that has to be the case because otherwise there would be further collisions. Yeah, okay, anyway, so we're showing that there are 3 collisions. What we'll see, we'll have to just identify each of the collisions and work through this formula to see, here we go, work through that formula to show what the final velocities will be, and then it'll show which the next collision will be. I'll give you an example. I'll run through the first one, and then I'll leave it up to you to work through the rest of them and yourself. So first of all, first collision, we're not going to have a collision between A and B because they're at the same velocity, so the collision will be between B and C. Okay, must be between B and C because B is moving and it's closer to C, and C is motionless, and there we go. So between B and C, so we know for the coefficient of restitution calculation, we can put a formula together for that. So 0.4 equals the difference in velocities after the collision. Now, this doesn't tell you which one you should subtract first, the final or the initial, and which one is the final or the initial. And in actual fact, I don't think it matters, but as long as you are consistent. So I'm going to do the ball on the right hand side minus the ball on the left hand side. So it'll be, this is the velocities after the collision, we don't know, so it's going to be VC minus VB, and divided by the difference in velocities before the collision. VC is 0 and VB is 4, so minus 4. Okay, excuse me. So we can get an equation from this, that's not an equals, that's a what's it's leading to, of 1.6 or negative 1.6 if we're being strictly speaking correct, which we probably should. Oh, hang on, did I do that right? Okay, I've just discovered that the marking schedule is not as consistent as I would have liked. It seems to make sure that you're dealing with absolute values on here, so it's using the highest number first. So VC will be the highest after the collision minus VB, and it'll be 4 minus 0 down here. I'll have to explore that a little bit more because I'm not particularly happy with that. Anyway, so we'll do it that way, ignore the absolute value things. It's going to be positive 1.6 equals VC minus VB. So that's one equation. We can form another equation, which will be the momentum equation, which is actually the velocity equation, because remember the masses are all the same. So we can just do the velocity of B plus the velocity of C equals 4. So now we have two equations and two unknowns, and we can simultaneously solve them for VB and VC. Once we know the velocity of B and the velocity of C, in fact I'll tell you what they are. So VC after the first collision is going to be 2.8 meters per second, and that's VC. VB is going to be 1.2 meters per second. They should add up to 4 according to our first equation. They do. So that means VC is faster than VB. Now for the second collision, we can see that ball A is going to catch up to ball B, all these letters, and then they'll have a collision, and you work through exactly the same thing here, simultaneous equation with the velocities conserved and with the restitution equation. And once you find out the final velocities of those, you'll then have a new picture with all three balls, and you'll have to see where the next collision will be, which I think you'll find is between B and C again, and then C will have a final highest velocity, then B, then A. And you can add up all the final velocities together, and it does in fact give you 8, so it shows it's all conserved. And that's how you do all of that.